All right, well, I will get started here. So you guys had questions about the homework? I heard somebody say they couldn't do, or got stuck on 108. Is that right?
It was me, yeah.
What was 108?
The velocity, acceleration, and that's all.
Of-
Find the position or something.
Oh, okay. So I'll do an example like that for you guys. So suppose you're given that the acceleration is like, oh, I don't know, t plus the sine of t. I'll do 2t there. Exciting. All right. And you're given that the velocity at time 2 is 3, and the position at time 2 is 7. All right? Then the question is, find v as a function of time and x as a function of time. That's equivalent to problem 108, right?
Yeah.
Because in problem 108, I give you acceleration as a function of time, and I tell you an initial position, and I tell you an initial velocity, and then I say to find the position and velocity as functions of time, right? So,
Yeah, something like
yeah, so it's the same problem, just different formula. So the key here is to notice that A is dv dt, right? By definition, the acceleration is the instantaneous rate of change in the velocity. But on the other hand, we also know that that's t plus the sine of 2t, right? So if I want to find v, what do? Well, I'm looking for a function that's derivative is this. And the antiderivative, right? So v is 1/2 t squared minus 1/2 cosine of 2t plus some constant I'll call c1. The half is there because if you want to think about it, when we differentiate cosine 2t, chain rule brings a 2 out, so I need the half there to cancel the 2 from the chain rule, right?
Yeah.
Or you could think about it in terms of a u equals 2t substitution, which ends up giving you dt is du over 2, if you want to think about it that way. But however you think about it, when we integrate sine 2t, we have to pull out a half, and we get minus cosine. All right. Now, we know that the velocity at time 2, right, is 3, right? But it's also equal to plugging 2 into this expression, which is, 4 over 2, find 2 squared over 2, minus 1/2 the cosine of 4, plus c1, right? So c1's kind of ugly, but c1 is equal to 3 minus 1, excuse me, 2 squared over 2 is just 2, right? So 3 minus 2 is 1, plus 1/2 cosine of 4, right? Then what? Then I have that dx dt is equal to v, right? But v is equal to, apparently, 1/2 t squared minus 1/2 cosine of 2t plus c1. And I'm going to leave c1 like that because it does not give me joy to rewrite this number another 5 times in the solution. Like, I'll put this back in our answer, but until then I'm just going to leave it as c1, okay? Because, it's easier to write c1. So again, I anti-differentiate, right? This time it gives me position. Position is 1/6 t cubed, right? Because a half times a third is a 1/6. And then minus 1/4 sine of 2t, right? Because when I integrate cosine, I get sine, but there's a 2, so I have to pull out a half in the anti-differentiation. And C1 integrates to C1t, and then there's the constant C2 here from this integration. Okay, C1 we already know. C1 is this number over here. It's 1 plus 1/2 cosine 4. Now what? Well, I also know that the position at time 2 is 7. So I do x of 2 equals to 7, and that's going to give me 8/6 minus 1/4 of sine of 4 plus 2c1, all right, plus c2. So c2 apparently is equal to 7 minus 4/3 plus 1/4 sine of 4 plus 2c1. So at this point, I think, guys, what I'm going to do is I'm just going to say this is C2, all right? This is C1. So solution V equal to, 1/2 t squared minus 1/2 cosine of 2t plus C1, and x equals to 1/6 t cubed minus 1/4 sine of 2t plus C1t plus C2, where C1 and C2 are given in star and star star. Hopefully your problem, the C1 and the C2 in your homework problem, are not this annoying. And when they're this annoying, feel free to use a calculator and replace this with a decimal. Whatever that is. I really don't know what cosine of 4 is off the top of my head. I think it's negative, but other than that, I can't tell you much. So, right, it would be completely acceptable to give a decimal form for C1 and C2 in this kind of problem, as to not have to write out this mess or that mess. Sadly, I have left my calculator downstairs, so I can't do that for us here. But what is it? Is it the algebra that's
Yeah.
troublesome, or? I mean, to summarize what we did, you take the acceleration, integrate once, it gives you velocity. Right? But when we integrate, we get a constant of integration. That constant, we can figure out what it is because we know the velocity at a particular time. So we plug in the velocity at a particular time, it allows us to solve for the constant, which I called C1 in this problem. So that gives us the velocity as a function of time. Then, since the velocity is the derivative of the position function, we integrate again to get position. In the process of that integration, that generates another constant of integration, which I've called C2. In order to figure out what that C2 actually is, you have to use the data which is given, which in this case is that x of 2 is 7.
Do we get the position when you integrate the velocity?
Yes. So a helpful mnemonic is something like this. Here's position, here's velocity, here's acceleration. To get from here to here, we differentiate. To get from here to here, we differentiate. To get from here to here, we have to integrate. To get from here to here, we integrate. And plus, initial condition. Plus initial condition. You need an initial condition to settle the integration constant. If you just integrate, then you don't, you're ambiguous up to the C1 and C2 kind of terms. So was there another problem in mission 8 that you guys were stuck on?
That was mission 7.
Oh, mission 7, my bad. But
One is the interval from 0 to 1,
mm-hmm.
square root of 3x.
Square root of 3x dx. Okay, so I'm going to do something very similar but different. So square root of 0 to 1, square root of, oh, I don't know, 9x cubed dx. So to do this problem, I just need to use properties of square root. So what are the properties of the square root? Square root of AB is square root of A, square root of B, right? So here we have integral 0 to 1 of the square root of 9 times the square root of x cubed. Square root of 9 is 3, right? And that's x to the what? X to the 3 halves. You see, because remember, the square root of x cubed is x cubed to the 1/2 power, right? Then how do I integrate? How do I integrate x to the 3 halves? I have to do what? I have to add 1 and then divide by that power, whatever it is. 3 halves plus 1, I believe, is going to be 5 halves, right? So we get 3 times x to the 5 halves divided by 5 halves, which is really just 6 over 5 x to the 5 halves. FTC2 says I have to evaluate from 0 to 1, right? And that just gives me 6/5. So your problem is very similar, right? You got square root of 3, you pull the square root of 3 out, then you have to integrate.
So we don't use the u substitution.
No. I mean, you could if you wanted to. You surely could. So, like, if I was going to integrate, I'll do a slightly different problem. Square root of, like, 4x dx from 0 to 1. You could use u substitution. You're not wrong. That's another way. So that would be u equals 4x, right? Du would be 4 dx. So I'm looking at integral of square root of u, right, times du over 4. And careful, we have to change the bounds, right? So it looks like the bounds in u are 0 to, oh, I'm an idiot. 4 times 1, not 4 times 4, dummy. Me, not you. So 4. So the bounds in u go from 0 to 4. And so I get 1/4 integral of u to the 1/2 power du from 0 to 4, which gives me 1/4. 1/2 plus 1 is 3 halves. Division by 3 halves is the same as multiplication by 2/3. So that gives me like 1/6, 4 to the 3 halves power. 4 to the 3 halves is 4 to the 1/2 to the 3rd, which is also known as 2 cubed, which is also known as 8. So that's just 8 over 6, which is, 4/3, right? So that's what that problem would look like with U substitution. If you did it without U substitution, if you just used algebra to do this one, it's easier. So I know once we have a hammer, everything starts to look like a nail, right? But sometimes a return to simpler ways is the right move. And like, I think this is an example of that. See, because if I go, I'm just going to go up here and do it. This would be equal to the integral from 0 to 1 of square root of 4 square root of x dx, right? Which would just be 2 integral of x to the 1/2 dx, right? Which is 2 times 2/3 x to the 3/2 evaluated from 0 to 1, which is 4/3. And I do think that that is easier in this case. So, but yeah, you could make a U substitution. That's also like a legitimate way to do this, like certainly. Other questions? Okay, well then, let me tell you a few more so tips and tricks. So I've shown you the basic things that we know about integration, the elementary integrals and then U substitution, right? And we've seen how to change the bounds and all that. There are a few other things that are worth knowing about. So here's the deal. If f of x is equal to f of minus x, all right, for x in, let's say, minus a to a, all right, then the integral from minus a to a of f of x dx is equal to twice the integral from 0 to a f of x dx. What is this condition that I've written? What's that called? This means f is an even function, right? And actually, in order for this to be true, I also need to know that f is like continuous, or at least piecewise continuous on the interval. If f had like a vertical asymptote, I could get into trouble here. Of course, technically speaking, that's like not allowed, since I've said that f of x is equal to f of minus x for all x in the closed interval. So that kind of says that the domain, it implicitly says to me the domain includes every point between minus a and a. But just to be extra clear, I should really assume f is piecewise continuous. So it can have points of discontinuity, but they better just be like jump discontinuities. All right. And infinitely many of those to avoid pathological cases. How about this, though? If f of x equals to minus f of minus x, right? Or a lot of times I'll write it this way, minus f of x for x in this interval, then what do we say about the integral from minus a to a of f of x dx? So let me draw a picture. If it's even, right, if this is the graph of the function at a, what does the graph to minus a look like? If it's even, it's a mere reflection across the y-axis, right? F of x is equal to f of minus x. So whatever happens here, the same happens there. So, you know, if I could do it worth anything. I'm not very good at mirroring, but I tried. It's supposed to be the exact same shape. The point is that this area and this area, they're equal, right? It's the same shape, just flipped over. So that's why you can just double the integral from 0 to a to get the whole integral for an even function. But what does the graph of an odd function look like? Yeah. Man, I'm bad at this. Root, 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 root. See, this area and this area, they're related. I mean, they're equal areas, but this one is, as a signed area, negative. And that one, of course, is positive. So when you integrate from minus a to a for an odd function, you just get 0. Does that make sense?
I would, I guess, 2 at first, but
Yeah, it's just because we're calculating signed area, they whatever's positive on the right becomes negative on the left and vice versa. Yeah. Yeah, now this allows you to write very obnoxious test questions that seem impossible, like example, integral from -1 to 1 of, you know, tanh cubed of x plus, you know, sine of x dx. So the thing is that the hyperbolic tangent of minus x is the hyperbolic is sinh of minus x over cosh of minus x, right? But cosh is even and sinh is odd. So we get minus sinh of x upstairs and we get cosh downstairs. In other words, it's minus tanh of x. What does this say? This says that tanh is an odd function. What about the cube of an odd function? Is it itself an odd function? Let's try it out. So how about tanh cubed of minus x? What happens there? Well, that's tanh of minus x cubed, right? By the calculation above, that's minus the hyperbolic tangent of x cubed, right? Which then, the cube of minus is minus, so we get minus tanh cubed of x, right? So therefore, tanh cubed of x is odd. By the way, the sum of odd functions is odd. It's easy to check. So what we have is an odd function plus an odd function. What's this integral equal to? The integral of an odd function about a symmetric interval of the origin. So the answer is just 0. Because we've shown that the integrand is odd. And, you can do kind of plays on this, like integral from, minus pi to pi of, I'll do tangent, tangent again. Let me do pi over 4 to minus pi over 4 of tangent cubed of x. All right. Plus, let's say, sine squared of x dx. We could do that problem. So essentially, by the same arguments in the previous, yeah?
James,
Uh-huh.
in the first example,
Yep.
that function is odd, but shouldn't it be like sinus that too? For it to
Oh,
be
yes.
zero?
So tangent cubed is odd, sine is odd, and the sum of odd functions is odd. So if we take two odd functions and we add them together, we still have an odd function. That might seem wrong to you, right? Because the sum of odd numbers is an even number. But that's a different use of the word odd. So bear with me here. If we have f of minus x equals to minus f of x, right? And we have g of minus x equal to minus g of x. So both odd, right? These are both odd functions. What happens when we add them? F plus g of minus x. What can we say about that? Well, that's f of minus x plus g of minus x, right? And if f is odd, that's minus f of x minus g of x, since g is odd. And then we can pull the minus out, and that's f plus g of x by definition. So what that shows you is that the sum of odd functions is odd. So this is odd, that is odd. So when we add them together, still an odd function. So be careful, this word odd, for arithmetic, yes, 3 plus 5 is 8. So the sum of odd numbers is an even number. But it works different for functions. The product of odd functions is an even function. So if I do like fg of x, of minus x rather, that's f of minus x, g of minus x, which gives me minus f of x minus g of x, which is f of x, g of x, which is by definition fg of x. So see, the product of odd functions is an even function, actually. So like, in contrast, the product of odd numbers, right? The product of odd numbers is likewise odd. So the role that additivity and multiplicativity play for even and odd numbers is opposite of how it works for even and odd functions. Which is, if you're not aware of that, it could lead to a lot of confusion, right? But yeah, the sum of odd functions is odd. With that said, does that make sense? I mean,
Yeah.
okay. My example 2 here is a mixed example. See, I've got two different things going on. I've got tangent cubed, which is, well, tangent is odd, right? You remember the graph of tangent. It's also sine over cosine, so almost for the same calculation as up here, erasing the h's shows you tangent is odd. But so tangent cubed is an odd function. But sine squared is an even function, actually, because it's the product of the sine times the sine, which is the product of odd and odd, which I just showed you is even. So sine squared is an even function. I'm going to wait, because I've stupidly written this right where I need to next work, so I got to wait.
Sorry.
No, you're fine.
So the plus or minus in the equation doesn't matter at all if it's
Oh, yeah, yeah.
odd or
That is very true. Very good point. If I put a minus here, it wouldn't change a thing. Just like I could put it here, 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 like that. Yeah. The sum or difference of odd functions is an odd function. That's also true for even functions. The sum or difference of even functions is again even. And in fact, the product of even functions is again even. So. Okay. So this one, we wanted to break into two pieces, see? Because we want to break it into two pieces because the one piece is odd and the other piece is even, right? And the odd piece, by the way, I don't think we can integrate in Calculus 1. I could be wrong, but I think that's above our pay grade in here. So you got pi over 4 to minus pi over 4 to pi 4 of tangent cubed x dx. That's 0 because it's the integral of an odd function about a symmetric interval of the origin. So this first piece is 0. And the second piece, what can we do? Well, I'll straight calculate it, but I'm going to show you tricks about how to think about that integral as well. In just a second here. So that's really twice the integral from 0 to pi over 4, right? Because it's even. So I can do the double up trick there. And what is the sine squared? Remember the trig identity? That's 1/2 of 1 minus the cosine of 2x dx. So the 2's cancel, right? And we're just left with x minus 1/2 sine of 2x evaluated from 0 to pi over 4. Which gives me pi over 4 minus 1/2 sine of pi over 2. And then when I plug in 0, I get nothing. So, man, that feels wrong. So I get pi over 4 minus 1/2. Is that right? That feels wrong. Feels wrong.
why did you change the integration from 0 to 4 pi instead of the negative 4 pi?
So that's because sine squared is even. I can use this theorem, if you will, this identity. I can double the integral from 0 to I'm sorry, the 2's cancel. 1 integrates to x. Cosine 2x integrates to sine, yeah. Divide by 2 because of the 2x there. Plug in pi over 4, I get 2. Yeah, pi over 2. Sine of pi over 2 is 1. Okay.
Sine is not 0.
What's that? Why is,
Um,
si-
in the beginning,
oh, why is this not 0?
yeah.
Oh, because this, if I do sine squared of minus x, right, I get sine of minus x times the sine of minus x, right, which is minus sine x minus sine x, yeah, which is just sine squared x. In other words, sine squared is an even function, so it doesn't integrate to 0, it goes to the other. So this problem uses both of the things I told you. Yeah.
Wouldn't the negative 1 half be negative 3 halves? Because the sine of pi over 2 is 1, and 1 times 1 half, 1 negative 1 half times 1.
No, negative 1/2 times 1 is just negative a half, though. Sorry, there's something bothering me about this. I don't know what it is. Okay. Consider this. So this is a kind of sneaky calculation. Sine squared plus cosine squared theta equals to 1, right? I'm going to show you this trick, and then I'm going to behave and get back on sort of standard topics. Okay, but just indulge me for this one here. So we all agree this, right? And so if we integrate sine squared theta plus cosine squared theta d theta, right, from 0 to 2 pi, well then surely we can agree that that's equal to the integral of d theta from 0 to 2 pi, right? Which is 2 pi. So this tells me, among other things, that the integral from 0 to 2 pi of sine squared theta plus the integral from 0 to 2 pi of cosine squared theta d theta is equal to 2 pi. But think about this. Sine looks like this. Cosine looks like that, right? So think about going from 0 to 2 pi. The values which sine and cosine take on over the entirety of the 2 pi period, it's the same set of values in the same shape. And then you're squaring them, right? So should these two integrals that I've just written, should they be different? No, they should be equal. So that tells me, so this is kind of the trick, right? Aha. So twice the integral from 0 to 2 pi of sine squared theta d theta is equal to 2 pi, which tells me that the integral from 0 to 2 pi of sine squared theta d theta is pi. Now, of course, you can actually do the calculation, right? You can actually integrate from 0 to 2 pi of sine squared theta d theta, you know? I'll do that over here. So let's see here. Instead of doing this, I do 0 to 2 pi, yeah? So pretty much everything here stays the same, except I got to divide by 2, right? Well, fine, I'll just erase. So I've got x over 2 minus 1/4 sine of 2x. Evaluated from 0 to 2 pi, what happens? You get sine of 4 pi or sine of 0 from the sine term, right? So when you evaluate the sine term at either of the bounds, this piece goes to 0. It's irrelevant. And so you just get 2 pi over 2, which of course is pi. But you can do more than this, right? Like, you guys tell me, what would be the integral from 0 to pi of sine squared theta d theta? If you start thinking about this idea that we're toying with. See, I know that the integral from 0 to 2 pi is pi, right? Think about this. If I go from 0 to pi, how is that related to the integral from 0 to 2 pi for the square of sine? See, if you square sine, it looks the same here and here, because when you square it, like the sine squared would look like this, right? Roughly speaking, this is sine squared. So the integral from 0 to pi is equal to the integral from pi to 2 pi for sine squared. Think about this. If the whole integral from 0 to 2 pi is pi, then the integral from 0 to pi is just pi over 2. It's got to be half of the integral from the whole thing. And then if you further accept this idea, what's the integral from 0 to pi over 2 of sine squared theta d theta? Is there any difference as you think about the shape here? 0 to pi over 2 versus pi. Is there any distinction between those? Right? I mean, left to right versus right. I mean, the shape is different, but if you look at the set of values that are attained there.
So it doesn't matter that the graph is under, like negative there.
Well, yeah, what I'm trying to say is, if I look at the graph of sine squared from 0 to pi over 2, it looks something like this, roughly speaking. And my point to you is this is the same as that. Like, let me use different colors. This area is the same as this area, which tells me that if I just integrate from, oh, this is 0 to pi, my bad. If I just integrate from 0 to pi over 2, rather than getting pi over 2 for my integral, I'm going to get pi over 4. So you can play these games if you can see a certain symmetry in your shape. If you know the integral over like the total shape and you can like see part of it as being a half or a quarter of the whole thing, then you can quarter the integral appropriately. But anyway, I don't know why I'm spending so much time on this. I just think it's fun. All right, so let's move on. Let us move on. So, our next topic. So, of course, you guys still need to work on your U substitution, right? So I have to make your next mission about that, right? So at the moment you have, I think mission 8 is mostly just on definite integration, but the integrals involved are not that hard, right? And then, so after that, I should give you a set of problems that are covering the different kinds of U substitutions like we did Tuesday. All right, so you should look for that mission 9, right? 9? I get 8, so that should be posted soon. Anyway, the next topic past that, though, is areas bounded by curves. You're like, well, didn't we already do that? Well, we did it in a special case. So let me show you a kind of typical example. Find area bounded by y equals x and y equals the square root of x. So pretty much all these problems, we have to come to some sort of graphical understanding of what we're doing. So this is y equals x. Just a line with slope 1, right? What's y equals square root of x look like? It's like half of a parabola that's turned sideways, right? It's like this. So we're trying to find the area bounded by these two curves. What area is that? Well, can you see it? Yeah, you see it. How do we figure that out then? What's this area? So the way I do it is I try to draw a typical infinitesimal rectangle. And so I'll draw a picture like this right here. Okay, there's my typical rectangle. And then I find dA for it. So here, dA is equal to the height of the rectangle times the width of it. What's the width? Well, the width is dx in this case, h dx. Well, now what's the height? The height, generically speaking, for this kind of rectangle is going to be the top y minus the bottom y. Which is the top, which is the bottom? Well, the top here is the square root of x. The bottom is x. So I've got x minus, I'm an idiot, square root of x minus x. So this is the infinitesimal area of that particular infinitesimal rectangle. Right? And then the concept is then you find that, and then to find the whole area, we integrate dA. So like A is the integral of dA. That's just a sort of heuristic I'm just writing. What does that mean? I mean, we integrate the formula for dA over the appropriate region of x. What's the appropriate region of x? The question is, where is the area? So I'll do the easy part. It starts at 0, right? What's this point of intersection up here? Where does the graph y equals x and y equals square root of x intersect? What is that? That would be where
x equals square root of x.
Where x equals square root of x. Very good. Now there's a chance that you were just going to tell me the answer, so I'm glad that didn't happen. I mean, you could guess the answer here. So how do you solve that equation? Square both sides, yeah? And that tells me that x times x minus 1 equals to 0. It has solutions x equals to 0 and x equals to 1. So we found out, aha, we already knew 0 just because we saw it. So the intersection points here are at 0 and 1. We can draw this infinitesimal rectangle. This makes sense for 0 less than or equal to x less than or equal to 1. That's where we can make this dA picture. And so we integrate from 0 to 1 of square root of x minus x dx. And let's see here, that's x to the 1/2. 1/2 plus 1 is 3/2. Divided by that is multiplication by 2/3. X to the 3/2 minus 1/2 x squared, and we evaluate from 0 to 1. FTC2. That's 2/3 minus 1/2 is what that is. What was that? 4/6 minus 3/6. So I think 4/6 minus 3, 1/6, 1/6. The area is 1/6. Somebody's used something wet on this board because it will not erase. Oh well. Example 2. So suppose we're looking at x equal to y squared minus 9, and y equals to x minus, I don't know, 3. That might work out nice. We'll see. Find the area bounded by these curves. Hopefully that problem makes sense. We'll find out soon. So, first of all, we'll draw the tricky part. X equals to y squared minus 9. That's a parabola that opens sideways. It has an x-intercept of minus 9, and it opens to the right. Let's see here. When x equals to 0, you got plus or minus 3. So I may need to change my line equation. We'll find out soon here. All right, that's x equals to y squared minus 9. It's this sideways opening parabola. Y equals x minus 3. I guess that's okay. Let's have y-intercept of minus 3, right? And slope 1. So that looks something like this. So where's the area? You see where the area that's bounded, right? Do you see the area bounded between these? It's in here, right? There's the area which is bounded. Now, this problem, we don't want to approach the same way we did the previous problem, because if we make vertical rectangles here, it's just unpleasant. All right? Like if I was to make a vertical rectangle, if I was to make my rectangles vertically, I would be using the parabola for both the above and below here, and I would be using the parabola for the up, but not the bottom. I'd have to break it into two cases. So what's a wiser choice of action here, all right? What's a wiser choice of action is to make your approximating rectangle look like this. Make it horizontal instead. So we want to find dA. All right, so what's the dA of this? Well, the thickness of such a strip will give in terms of dy. And we want to talk about the width times dy. Y, not w. What is the width of that? Well, it's going to be the right x minus the left x, right? what's the right x, what's the left x? We need the formula in terms of y for both of those. See, once I write that dy, that means that I'm going to end up doing an integral in terms of y. So I want functions of y to describe my x's. So the yellow one, I've got, x equals to y plus 3, right? That's the right x, isn't it? That's the one that's on the right. Right? You see it? So if I look at this, this is the line y equals x minus 3. Solve for x, I get x is equal to y plus 3. So I've got, y plus 3. So I've got y plus 3 for the right x. How about the left x? Well, the left x is this guy, right? And so you could say xl is y squared minus 9. So minus parentheses y squared minus 9 dy. And so what that gives me, of course, is, 12 plus y minus y squared dy. But now the question that's a little bit less obvious, for what y have we drawn that rectangle? See, because this makes sense from where? From this point all the way up to that point. How do you find these points? Because those points are what informs us what we should integrate to and from, So you can look for x, xl equal to xr, so to speak. So in this case, that's, y plus 3, rather y squared minus 9 equal to y plus 3. And so that's y squared minus y minus 12, I believe, equal to 0. Can you solve that? Let's see here. How about y? I think that might actually factor, because 12 is 3 times 4, but we need a minus 12. So we need one of the 3 or the 4 to be minus, but the minus wins. So we do minus 4 plus 3, yeah? Yeah, that works. So looks like we've got y equals 4 and y equals minus 3 as our points of intersection, right? In other words, this was, right here, this was at minus 3, and this guy up here is at 4. So here we go. The area is the integral of dA, right? We take the continuous sum of the dAs, but what that means here is that we go from minus 3 to 4 of dA, but dA was what? It was 12 plus y minus y squared dy. And now we just have to do the integral, which we can do, Like, once you get to the integral, it's a walk in the park, right? Which is what? That's 12y plus 1/2 y squared minus 1/3 y cubed. You got to take that. You got to evaluate from minus 3 to 4. So that gives us 12 times 4, which is 48. 4 squared is 16. 16 over 2 is 8. And then 4 cubed is 64, so that's minus 64 over 3. That's from the upper bound.